we're going to talk about Markov decision processes. This is a very, very interesting and exciting topic, at least to me, because it's a precursor to reinforcement learning. We're going to talk about non-deterministic search now. What do I mean by non-deterministic search? I mean search in settings where the outcome of actions are not necessarily known. If you decide to go forward, you don't necessarily end up in the forward position. You may actually go left or right and such. Let's look at a simple example, the grid world. It's a maze-like problem. There's an agent. Here's our agent, if you can see my mouse cursor. In a grid environment, there are walls that block the agent's path. So just like our previous example, I can't remember what it was called, the game, Pac-Man. It's like Pac-Man, the agent cannot go beyond the wall. So if the agent is at position 3, if it tries to go back, it will remain where it is. Now, we consider this environment as a noisy environment because actions do not always go as planned. For example, 80% of the time, the action north takes the agent north, if there is no wall there, of course. 10% of the time, north takes the agent west, and 10% of the time, the action going north takes the agent east. If there is a wall in the direction, the agent would have been taken. The agent stays put, stays in the same location. Now, another interesting property of this environment is the agent receives rewards each time step. So at each time step, the agent may receive a small living reward. The agent has not died yet. It can also be negative to represent the fact that we want the agent to get to the goal, to the diamond. You see that blue diamond up here faster rather than later. And big rewards come at the end. The big rewards can be negative big rewards, dying in a pit fire, or getting the diamond, a positive reward. What's the goal here? Remember, our agents are goal-driven. The goal is to maximize the sum of rewards. So we are not just interested in maximizing instantaneous rewards, but we want to maximize the total sum of rewards that the agent gains throughout its interactions in this environment. Now, let's look at what we mean by non-deterministic actions or stochastic settings. In a deterministic setting, if the agent wishes to go north from this position, it will end up in the north position every time. But in the stochastic grid world, if the agent decides to go north, well, it's not sure that it's actually going to end up in the north position. There's an 80% chance that it ends up here, but there's a 10% chance that it ends up in the pit fire to the west, and 10% chance that it ends up in the east location. This is what I mean by stochastic settings in the grid world. Now, how can we model these settings? One approach, the most popular approach, I must say, is the Markov Decision Processes Framework, or an MDP. An MDP is defined by a set of states S, so this is so far similar to what we had in our search problems. A set of actions, A, what actions are available to the agent it may be state dependent, a transition function, which says the probability of ending up in state S prime if you are in state S and you take action A. So in other words, the probability that taking action A from state S leads to S prime. Remember, this is a stochastic environment. So this probability is not always 1. If you decide to go north from this position here, the probability of ending up at north is not 100%. It's less than 100%. That's why we call it a stochastic setting. This transition probability or transition function is also called the environment model or the dynamics of the environment. These two terms are used interchangeably with transition function. Now, there's also a reward function, R, which tells us how good it was for the agent who was in the state S and took action A and ended up in state S prime. So going from state S to state S prime by taking action A generates an instantaneous reward and is captured by this function R. Sometimes this R is only dependent on the state S or the next state S prime. There's also a start state. When you're defining an MDP, you often need to specify which state you're starting from, just like our search formulations. And there may be a terminal state, one or more terminal states. So if this agent here gets to this state, or this state, if you can see my mouse cursor, if the agent gets to either of this fire pit or the diamond, the episode ends. So the interaction ends. The agent either gets the diamond or dies in a pit of fire. But that's not always the case. There are settings where there is no terminal state. The interaction keeps going. It's interesting to look at MDPs as non-deterministic search problems. What are we searching for here? We're searching for something that tells our agent how to act in each state. We'll formalize it later on. But it's important to know that MDPs are essentially search problems of the non-deterministic kind. Now remember, the M in MDP stands for Markov. What does Markov mean? Markov generally means that given the present state, the future and past are independent. Okay, let's decipher this statement a little. In Markov decision processes, the word Markov means action outcomes depend only on the current state. If we want to know what the next state is going to be when we are in the current state and we take a particular action, we don't need to know what our previous states have been. If I'm at location 0 and I take action go forward, we don't need to know what my previous locations have been to figure out my next location is going to be location 1. I really wish I could do a fully physical demo for you, but we are constrained by the limitations of online presentation. Mathematically, the probability of the next state, S sub t plus 1, being S prime, given the current state being S sub t, the action taken at this step being A sub t, and st minus 1, the previous position, not the current position state, is st minus 1 and so on, is equal to, just get rid of all of these previous positions, p of s sub t plus 1 equals s prime, given the current state and the current action. So if we want to know what the probability of ending up in a state S prime is, all we need to know is the current state and the current action. We don't need to know what the previous states were. That's what the term Markov means in MDPs. This is just like search, where the successor function could only depend on the current state, not the history. Now, I'm going to pose a question here. I want you to chime in by raising your hands first. Is our world Markovian? Does the next state of the world depend only on the current state? What do you think? Let me see. We have Shantanu. Shantanu, go ahead. Hello? Okay, I can't hear you. I believe Satish has his hand up as well. Satish? You can unmute your microphone and tell us your thoughts. Okay, that's interesting.
It's a Markov process, I think so.
And why is that?
Because like everything in the future will depend on the present action only, I believe.
Is that really true? It depends on the present action, of course. But what about our history? The fact that I'm here right now depends on, is rooted in where I was born, how I was educated, and what I did before joining the university and what I did last week as well, right?
Yeah.
So let me see if there's anyone else who'd like to participate. Venkatesh?
Comes to weather prediction or anything else, it's going to be, it doesn't consist of any Markov chain process, but if it comes to real-time factors, it will be Markov.
Can you expand on that? What do you mean by real-time factors?
That means future grain prediction or something else like that. If you are predicting the weather, it's not going to be a Markov chain process, because we are taking the past history data, so that's why it won't be a Markov.
Okay.
But what you gave the example, actually, the things are already done. It doesn't consist of any Markov.
All right. So for the interest of time, thank you to all of those who raised their hands. So I'm going to answer this question. It depends. It depends on how we represent the state, right? So the fact that I'm teaching this class right now is, of course, dependent on my background. But that background can be summarized in the state of my neurons, right? So if my state is represented as the values or the parameters of my neurons, all of the history of my life is already summarized in the current state. So in most cases, it is possible to come up with Markovian state representations of dynamical systems. Some state representations are not Markovian. Like, can you think of an example for a non-Markovian state representation, Zishan? Zishan? Okay, I can't hear you, Zishan. Anybody else? Vivek?
Do you mean the real, do you mean in the real world life state, like example in the real world?
I'm sorry, I didn't catch that.
So do you mean the non-Markovian process examples in the real world or something else?
Yes, but the question is not non-Markovian process examples, non-Markovian state representations in the real world. So see, Markov is dependent on how you represent the states, right?
Yeah, yes.
Okay, so do you have an example in mind?
No, not right now.
Okay. So let me see if anybody else have their hands up. Venkatesh?
So can we consider stock market as non-Markovian?
Well, what's your state representation here?
So current stock rate?
That's correct. So if you're only looking at the current stock value, that state representation is non-Markovian because the future value of the stock does not just depend on its previous value, right? That's a very good example. Thank you very much.
Thank you.
But if we were to represent the stock market settings or the state of a single stock as its current value as well as its rate of change, then it would convert the process or the state representation into one that accommodates the Markovian assumption. As we move forward, you will see more examples of Markovian representations, but an important takeaway from this slide here is first the definition of Markovian, and second, the fact that almost all non-Markovian systems or state representations can be converted into Markovian state representations. Ramu, do you have a question?
Like if flipping a coin comes under Markovian or non-Markovian?
What was that?
Flipping a coin.
Flipping a coin, how do you represent the state?
Maybe a heads or a tails.
So yes, if you represent the state as heads or tails only, then it's not Markovian. But if you represent the state as, well, heads or tails, the current state, as well as all of the parameters of the environment, like the air pressure, the gravitational pull, and the flipping force vector, then the process becomes Markovian, because having those parameters as well as the current state would be sufficient to predict the next step. Here's a very important takeaway. The takeaway is non-Markovian state representations can often be converted into Markovian state representations. Okay, so let us continue. Ramu, you might want to lower your hand, unless you have a question. Okay, let's continue. Now, let me define a new concept, and it's a concept of policies. In deterministic single-agent search problems, if you remember, we wanted an optimal plan, which was a sequence of actions from start to a goal. For MDPs, what we are looking for is an optimal policy. The policy is a function, and it's usually denoted by pi, that maps the states to actions. It tells you what action to take when you are in a particular state. An optimal policy is one that maximizes expected utility if followed. Remember the notion of utility? We've talked about it a couple of times so far. We're going to expand on it in a couple of slides. The optimal policy is one that maximizes expected utility. An explicit policy defines a reflex agent. Remember reflex agents, those that just reacted reflexively to the state? The policy is essentially defining a reflex agent. It tells the agent what to do for each state. Now, Expectimax, if you recall, didn't compute entire policies. It only computed the action for a single state only. It essentially told us that if you're in this state, you need to take this action to go to the next state. Now, these are examples of policies, right? See, it says if you're in this state here, what you need to do is to go left. If you're in this state here, what you need to do is to go left. If you're in this state, go up, and so on. This is going to be a quiz later on, but given that being in each of these states, except the terminal states, has a particular value, for example, being in this state, has a being in this setting, being in each of the non-terminal states has a value of negative 0.01. This is similar to the living reward. Every second that you live gives you a negative value of 0.01 unless you're in one of the terminal states. How can we see whether this policy is optimal or not? Think about this problem, and then later on you'll see how to evaluate the policy given these given this reward function for non-terminal states, and then we'll see whether these policies are optimal or not. I will expand on it with more examples later on. This was supposed to be a quiz in a physical class. Let's go into a more illustrative example. A robot car wants to travel far quickly, but we can represent the racing settings of that robot car with 3 states. The car can be cool, or it can be warm, or it can be overheated. There are 2 actions available to this robot car. Go slow or go fast. Going faster gets double reward. Now, let's see how we've represented this state. If the robot car is in the cool state and it goes slow, the transition probability of remaining in the cool state is 1. See, this arrow here refers to a transition, and the fact that it comes back to this state means that if the car is cool and goes slow, it remains in the cool state and will get a reward of +1. This value here, 1.0, is the probability of this transition occurring. Now, if the car is cool and it performs the action fast, it goes fast, with probability 0.5, with 50% probability, it may end up in the warm state, but gets a reward value of +2. However, with probability of 0.5, 50%, the car may remain in the cool state and still get this reward of +2. Remember, going fast gets double reward. Now, when it's in the warm state, if it goes slow, with probability 50%, it ends up in the cool state and gets a reward of +1. And with probability 50%, it remains in the warm state and gets a probability of +1. However, if the car is in the warm state and goes fast, it will definitely end up in the overheated step and crashes and gets a very low reward of -1. Now, we have this setting. We know how to formulate it. We can even represent it as a search tree. Remember search trees? Remember the fact that MDPs are also representing search problems? Let's see how we can create a search tree for these settings. So the car is in the cool mode, and it may remain slow. It may go slow and remains in the cool mode or state, or it may decide to go fast. See, this is a red arrow representing going fast, and will either end up in the cool state or the warm state. These circles here, these green circles represent chance, if you recall. And we can keep going and keep representing this setting with the same terminology, with the same tools that we use to draw the Expectimax graph. Now, to further solidify our understanding of MDP search trees, we need to think of these as Expectimax-like search trees. There is an agent who's always trying to maximize something. Remember, the upward pointing triangle is the maximizing agent. When the agent in state S and performs an action A, it ends up in a chance node represented by the Q state. We call this a Q state, which represents the fact that the agent was in state S and performed action A. And then it may end up in state S prime or other states. This here, this arrow here, is called a transition. Now, how likely it is for the agent to end up in state S prime is determined by the transition function, or the transition probability, the probability of ending up in state S prime if you are in state S and have taken action A. Why do we have chance nodes here? Well, because we're dealing with non-deterministic. We are dealing with stochastic search problems. We're not certain that if we are at state S and we take action A, we'll end up in the state S prime. there's an element of chance involved here. Now, remember we mentioned we defined optimality of a policy as maximization of utilities, maximization of expected utilities. We are now going to go deeper into the definition of utilities and utilities of sequences. The question here is, if we have multiple sequences of actions available to us, which one should we prefer over the other? How are we going to evaluate those sequences? Are we going for one that gives us more rewards now compared to those that give us more rewards towards the end? So let's see, one sequence of actions ends up giving us a +1 reward in step 1, +2 reward in step 2, and +2 reward in step 3. If you sum it up, you'll see that it gives us a total reward of 5. The alternative is to get a reward of 2 now, reward of 3 in the next step, and a reward of 4 in the step afterwards, which gives us a total reward of 9. Which of these two would we pick? The one that gives us more total reward. That's the definition of rationality. But do we want the reward now or later? So which of these is better? Getting 0 now, 0 in the next step, and 1 in the final step, or getting 1 now, 0 in the next step, 0 in the final step. Out of curiosity, how many of you would go for this option? 0 now, 0 in the next step, 1 in the final option. Raise your hand if you would go for this option. Okay. How many of you would go for now, lower your hands now. How many of you would go for this option, the one that gives us a reward of 1 right now and 0 in the future steps? Anyone? Okay, Archana, would you like to explain why you preferred this option over the other one?
Because at the first I get something and later if I don't get, then I won't be disappointed.
Disappointment. That's a very good point. So here's the thing. Remember, we're dealing with the stochastic settings. If we get a reward of 1 now, or if we are starting in this position here, and we know that the next step is giving us 1, let me rephrase this. This option here is telling us that it is possible in the beginning. It tells us that it is possible to get this reward of 1 in 3 steps, but it's not definite, right? Because we're dealing with probabilistic settings. We're dealing with non-deterministic settings. This option here is telling us that you're going to get this 1, that's for certain, but you may get 0 in the future steps. So a rational agent would assign more value to the rewards that come with more certainty. And in sequential decision making, this typically, the more certain rewards are those that happen sooner rather than later. We'll dig deeper into this in a couple of slides. So it's reasonable to maximize the sum of rewards instead of instantaneous rewards for a rational agent. It's also reasonable to prefer rewards now to rewards later because of the stochasticity. We don't know whether the rewards that we expect to happen in later steps will actually materialize. So one solution or one approach to account for this preference of sooner rewards over later rewards is to decay the values of rewards exponentially over time. What do I mean by that? A diamond now, getting a diamond now may have a reward of 1. But if we expect to get it in the next step, its value is going to be multiplied by a discount factor, gamma. This discount factor is less than 1. It's a value between 0 and 1. So in the next step, the value of the diamond, the expected value of the diamond, is going to be less than 1. It's going to be gamma multiplied by 1, and gamma is a value between 0 and 1, which means that the worth of this diamond, the expected worth of this diamond, is going to be less than what it was for us if we were to get it now. Now, I mentioned that we are decaying exponentially. So in 2 steps, the value of the diamond is going to be gamma multiplied by the previous value, which was gamma. This is going to give us gamma squared. And it's going to be less than this other 2 values. Why? Well, what's 0.1 multiplied by 0.1? It's 0.01, right? 0.01 is smaller than 0.1. So gamma squared is smaller than gamma. What's the point of exponential decay with this discount factor here? We are implementing this idea that we prefer rewards that happen now to rewards that happen later. If we were to get this diamond now, it would be worth 1 unit for us. If we expect to get it in the next step, it's going to be worth a little less. Gamma can be 0.99. So instead of 1, this would be worth 0.99. When we are thinking about the future reward, we are discounting the worth or the value of the reward because we are not certain we are going to get it. We are just going to say it's worth less if it happens further in the future rather than sooner. So just to further explain the concept of discounting, consider the MDP tree. At each time that we descend a level, so at each time we go from this level to the other level to the next level, we multiply the value of the reward in the discount once. So the value or worth in the first step is 1. Now that we go to the next step, we multiply 1 by the discount factor. It becomes gamma. And then when we go to the next level, it becomes gamma multiplied by gamma, which becomes gamma squared. Why do we apply this discounting scheme? Well, it's because sooner rewards probably do have higher utility than later rewards, because we're not certain that we will achieve the rewards that we expect to happen in the future. There's also a perk, a hidden perk in discounting. It helps our algorithms converge. We'll talk about this later on. So for example, if we have a discount factor of 0.5, the utility of these sequence of rewards, these expected sequence of rewards, becomes 1 multiplied by 1, because 1 is happening now, plus 0.5, this is the discount factor, multiplied by 2. This 2 is expected to happen in the future, and it's happening in the next level, in the next step. That's why we are multiplying it by 0.5. What about this 3 that we expect to see in 2 steps? It will be multiplied by 0.5 to 0.5 squared, which is 0.25. So you can see that the utility of getting this sequence of rewards, first 1, then 2, then 3, is less than the utility of getting this sequence of rewards. First 3, the larger reward, then 2, then 1. Any questions about discounting? Venkatesh?
Professor, instead of using this discounting, we can use the search trees also, right?
We can use what?
Search trees, expecting max.
Okay, tell me more.
So you keep on discounting with the item value, it will be, the utility will be reduces, right? The maximum utility will be reduced.
So in expectimax, we are not changing the value or worth of terminal states, right?
Yep. Yes.
In here, what we are saying is, if we get a value of 3 in 3 steps, it's going to be worth more to us than if we were to get the same value in 10 steps.
Okay.
Right?
Yep.
Okay. Any other questions?
No.
Venkatesh, can you mute your microphone?
Sorry.
Thank you. Any other questions? Okay, so let's continue. Now I'm going to talk about something called the assumption or theorem of stationary preferences. It says that if we have a sequence of rewards, rewards A1, A2, all the way to AN, and we prefer this sequence of rewards to another sequence of rewards, B1, B2 to Bn, then if we shift the rewards by 1 step to the right and have a different reward greater than 1 in the first step, we still prefer the first sequence over the second sequence. This is called the theorem of stationary preferences. So what's the point of this? It says, if the preferences are stationary, and I'm going to tell you more about the common interpretation of this in economics. If the preferences are stationary, then a rational agent can define its utilities in only 2 ways. One is additive utility, just add the rewards obtained in each state, or discounted utility, R0 plus a discount factor gamma multiplied by R1 plus gamma squared R2 and so on. These are the only 2 options available to a rational agent dealing with the stationary preferences. Now, what's a common or economical interpretation of stationary preferences? It means that over time, your preferences of certain states are not going to change. In other words, the reward that you're going to receive from certain states are not going to change. For example, if you get $1,000, if you get $100 per day, let me think of a better example. So if one sequence of preference, all right, here's a better example. You will always prefer $100 to $99, right? This is the assumption of stationary this is an example of stationary preferences. You will always prefer $100 to $99. Is that necessarily true? Vivek? Vivek? You're on mute.
Yeah.
All
So
right.
it depends upon the condition when you're going to give me the money. If you're offering me $99 right now and $100 after a month, I'll take $99 right now rather than getting $100 after a month.
So yes, that's a notion of preferring things happening now over the future. That's of course one condition of it. One more thing is, if I'm really rich, if I'm a billionaire, if I become a billionaire, like tomorrow, if I win some weird lottery that gives me $1 billion, then there will be not much difference between $100 and $99 for me. I may be indifferent to the difference of $1 if I'm a billionaire. If I become a billionaire, then my preferences are no longer stationary. This change of me becoming a billionaire has changed my preferences. So my preferences are no longer stationary under the assumption that I may become a billionaire and assign different worth, different values to different outcomes. There's a deeper discussion on the stationary preferences. I'm going to share a conference talk by a colleague of mine on rationality and the stationary preferences. It's going to be optional. But what I want you to take away from this slide here is a rational agent dealing with stationary preferences can only represent the utilities in two forms only, either simple addition or through discounted utility. Now, we'll go over this quiz later as an example in the tutorial. What if the game lasts forever? What if there is no end to the game? Do we get infinite rewards? Remember, we had two options for representing or defining utility. Either add the rewards up or add or apply discounting in getting the value of utility. So if we go with the first option, non-discounted summation, what would happen in infinite settings? Would we get infinity as our utility? Well, yes, if we don't apply proper discounting, as you'll see. What are the solutions to this problem? One solution is to apply is to constrain the horizon or make the horizon finite, the time horizon finite. This is similar to limiting the depth of search. This is similar to depth limited search. We can terminate episodes after fixed T steps, very similar to life. Our lives are all non-infinite episodes. We are all going to die. This is, I know that it sounds depressing, but it's actually very powerful when it comes to optimal decision-making and coming up with optimal policies. Alternatively, and also, there is a problem with limiting the horizon, the time horizon of an infinite sequence or episode. It gives non-stationary policies. So the policy, which maps states to actions, if it's derived from a finite horizon setting, will depend on the time left. So the policy will be time dependent. It will not depend on the state only. Remember, pi was a function of state, but when we derive it from a limited horizon or a finite horizon setting, it will no longer depend on S only or the state only. It will depend on the remaining time as well. The other solution is discounting. it's interesting. You can show that infinite series of this type, gamma to power t, and t is the time step, multiplied by a scalar reward, is always going to converge to a non-infinite value. It's going to converge. It's going to, this infinite series is going to converge to a finite value. The upper limit of that value is determined by this ratio here. It's the maximum value of the summation is the maximum reward that can be achieved in any state, and this is the instantaneous reward, divided by 1 minus gamma. A very, very important thing to note here is this assumes that gamma is between 0 and 1, and it excludes 1. So if gamma is 1, this turns into the non-discounted summation and will not converge. It will keep going towards infinity. If gamma is 0, what will happen then? Anyone? What happens if gamma is 0? Satvika?
The utility will be 0.
Interesting. Not quite. 0 to power 0 in some settings can be considered to be 1 because we assume that everything to power 0 is 1. So in the very first time step, 0 to power 0.
Then it would be 1.
Then it would be just the immediate reward in the very first step, which is not very helpful. Thank you, Satvika. That was a good answer. Thank you. Now, what does this value of gamma represent? It represents how much we value things that happen later in time. Smaller gamma means smaller horizon. It means that we are myopic. It means that we care a lot more about things that happen soon rather than those that happen later in time. Of course, a larger gamma, a gamma close to 1, means that we care more about the rewards that we expect to happen later in time. Another solution to the infinite horizon setting is putting in or defining or finding an absorbing state, which guarantees that for every policy, a terminal state will eventually be reached. It's like overheating for racing. So remember the settings of racing? Let me go back to the slide. Is this a finite horizon problem or an infinite horizon problem? How many of you believe that it's finite? Raise your hand. Okay, now lower your hand. How many of you believe that this is an infinite horizon problem? Okay, Kuntang, would you like to explain why you think this is an infinite horizon problem?
Because it may be last forever, cool on and run forever.
Yes, that's correct. Thank you. You can all lower your hands now, and Kuntang, you can go back on mute. So here's the thing. If the car always is in the cool state and always goes slows, then this never ends. It will always remain cool and things will go on. Even if the car decides to go fast, it can still decide to slow down, and there's a chance that it will be stuck in a cycle between cool and warm forever. So right now, there's no guarantee in these settings that the episode will terminate. It may go on forever and ever and ever. This is why this is an infinite horizon problem. Let me go back to this slide here. Now, if we can guarantee, if we can show that over time, a terminal state like overheating, the overheated state, will eventually be reached, then we can solve the problem of infinite utilities. This is not possible for all problems, for all settings. For example, for the racing settings, the current parameters and the current values do not guarantee that the terminal state of overheated will be reached. So let's do a quick recap. We defined Markov decision processes, and we enumerated the parameters of an MDP, which are states, set of states S, the start state S0, set of actions A, the transition function or the transition probability or the dynamics of the environment, P or T, these two are equivalent. P represent the probability of getting to a state S prime conditioned on the fact that the agent is in the state S and takes action A. The T function is equivalent to this one. It's just a different representation. And there's a reward function, instantaneous reward function, R, and possibly a discount factor, gamma. This gamma is typically a constant throughout the interaction of the agent or the decision-making process. There are research studies, including one in my own lab, that try to develop schemes for adaptive discounting. But in general, discounting in MDPs is based on a constant value of gamma. So if you choose gamma to be 0.99, it will remain 0.99 throughout the problem and its solution. We've also defined two quantities in MDPs. We've defined a policy, which is a function that maps each state to a corresponding action. It tells the agent what action to take when it's in a particular state. And we've defined utility as the expected sum of discounted rewards. That expected bit is really important because we're dealing with probabilistic settings. Remember Expectimax and our discussion of expectation. Remember, the expected value is the weighted average, and the weights are probabilities of occurrence. Now, how do we solve MDPs? So what does it mean to solve an MDP first? It means to find the optimal policy. What's an optimal policy? An optimal policy is one that prescribes actions for states such that the total sum of rewards are maximized. Not just instantaneous rewards, but the total sum of rewards. So to talk about or investigate solutions to MDPs, we need to define a few more quantities. We'll first define the value or utility of a state represented by the function V of state S. Remember, star or asterisk in this course represents optimality. So the optimal value of a state S is the expected utility of the agent if it starts in state S and follows the optimal policy. So it tells us how good it is to be in a particular state S if we already have the optimal policy. Then we define the state action value, or the Q value of being in a state S and performing an action A. So the Q value for state S and action A is the expected utility of the agent starting out at state S by taking action A and thereafter acting optimally. So it's essentially telling us that it's telling us how good or useful it is to take action A in state S. How useful it is, for example, if you're considering a navigation problem, when you are stopped in front of a red light, so the state is you're stopped and you're in front of a red light, what are the possible actions? Moving forward or staying where you are. You can actually evaluate the value of moving forward when there's a red light and the value of staying in the same place. Typically, the value of moving forward when there's a red light should be lower than the value of staying put. This is what the Q function is telling us. The Q function is telling us how good it is, how good an action, a particular action A is when you're in a particular state S. Now, let's define the optimal policy as well, redefine it in different terms. The optimal policy, pi star of S, gives us the optimal action to be taken from state S. And we've already defined optimality as the maximization of total expected reward. So let me show you a quick demo of this here. In the grid world, where there's a 20% chance, this is noise, a 20% chance that the actions go wrong. If you want to go north, there's a 20% chance that you end up in a different place, 10% chance of ending up east, 10% chance of ending up west. Considering a discount factor of 0.9 and a living reward of 0, so being in each step does not give us anything. There is no reward for being in each of these non-terminal states. You can calculate the value of each state accordingly. It will look like this. We will go over the algorithm for this calculation in a couple of slides, but you will see that each state here has a particular value. These two are terminal states, very similar to minimax and expectimax. These two remain the same. When you get to these two states, you will get these values, get these rewards, and things end. Now, let's see how good it is to be in this state here. When you're in this state, if you decide to go right, go east, there is an 80% chance that you'll actually end up here, right? So you can say the value of being here is directly related to the value of this one here multiplied by the probability of getting it, which is 80%. These values are not final, by the way. You see that we've obtained these after 100 iterations. We can continue iterating. You will see the iterative algorithms in a couple of the slides. These values are not final yet. But you can see that it's better to be in this state rather than this state here. If you're in this state, you will have to, the chances of you getting to the optimal a reward, optimal sum of reward, is lower than if you were here. Why? Well, imagine you're in this state and you decide to go west, go here. There is a 10% chance that right here, you will end up in the pit of fire, -1. That's why this is not a very good state to start with. But anyways, it's just telling us comparatively how good it is to be in each state. Let's look at the Q values as well. So each of these quadrants is the value of taking a particular action in the corresponding state. So if you're in this state here, you have 4 actions available to you. You can decide to go north, and the corresponding value of going north in this state is 0.77. You can decide to go south. The corresponding value is 0.57. You can decide to go east. The corresponding value is 0.85. Or you can decide to go west. The corresponding value is 0.66. So which of these would a rational agent choose? The one that has the highest value, the action that has the highest value, going east. What about this state here? There are 4 actions available to the agent. It can go north, and the value of taking action north in this state is 0.57. It can decide to go east. The value of taking this action is -0.6, and so on. And the highest, the action with the highest value is going north, right? Why is this value not -1? Why is this value, the value of being in this state and taking the action going east, is not -1? Can anyone answer this question? So let me ask you this. If the agent is in this state and decides to go east, does it necessarily end up in this location here in the pit of fire? Well, the answer is no, because we have a stochastic environment. There's a 20% chance that it will end up somewhere else instead of here. That's why this value is not -1. Okay, any questions so far before I go into mathematical formulations of the value function and the Q function? Bibek? Bibek? You're on mute again.
Yes, sorry.
No worries.
What determines the randomness, that noise 0.2?
So in this example here, we've determined this randomness because we are designing the environment ourselves. You're saying that, hey, there is a 20% randomness involved in actions. What about in the real world? You will see later on that in the real world, since we don't have exact models of the dynamics, sometimes things don't go as expected. Remember the example of a 2-wheeled robot which decides to move forward, so rotate forward the wheels, but it may hit a stone. One of the wheels may hit a stone, and instead of going forward, it will rotate to left or right. Since hitting a stone is not always predictable, we can consider it a chance event. We can say that whatever action we take is not it's not deterministic that it will do what we expect it to do. Something may go wrong. We may have not considered some of the parameters in the environment, which is very likely in real world settings. Does that answer your question, Bibek?
Yes. I have another question. That Q values after 100 iteration, what does that mean? Like, have you already went through all those steps and determined those values?
I'll explain that in a couple of slides. It follows an iterative algorithm called value iteration and Q learning. We'll talk about this in a few slides.
Thank you, Professor.
Sure. Any other questions? And Vivek, you might want to lower your hand. Okay. Very well. So how do we evaluate the value of states? How did we come up with these values? Well, the fundamental approach or the fundamental operation here is to compute the expected max value of a state, right? We already have this tree representation, and we already know of an algorithm that can solve these sort of problems called expected max. So the idea here is to find the expected utility under optimal action. And it's going to give, and then we calculate the expected utility as the average sum of discounted rewards. And this is exactly what expected max computed. How can we come up with a more rigorous and efficient formulation? Well, note that the optimal value of S, of a state S, is equal to the maximum value of Q, maximum Q value of S, which is the value of the action that maximizes this value. This is what max over A means. It means that we are looking for the maximum value of Q star, and we are looking for an A that maximizes this value. Later on, we'll see the argmax operator as well, and I'll explain what that is. So what's the value, optimal value of a state S? It's the same as the optimal Q value of a state S if the action chosen is the optimal action that can be taken in that state. Now, what's the Q star itself? We can define Q star of being in state S and performing action A as this here is the probability of being in state S, performing action A, and getting to state S prime. This is the transition probability of reaching to state S prime. This is the instantaneous reward that the agent would get if it gets to state S prime. And this here is the discounted sum of future rewards, which is the value of state S prime. So this here should be self-explanatory. The Q value of state S and A is the reward that the agent gets by getting to the next state, plus the discounted sum of the remaining rewards obtained if the agent acts optimally. That's from the definition of Q star. What's the sum here for? We are summing over S primes. It's because we don't know what state the agent is going to end up in. Remember, we are dealing with stochastic settings. So it may end up in different states. If it's in state S and takes action A, it may end up in different states. That's why we are calculating this value for all of the states that can be reached from being in state S and taking the action A. Note that this here is a probability, right? What do we call a summation of outcomes multiplied by their probability of occurrence? Anybody? Venkatesh?
Oh, maximizing the value.
Well, maximizing this is maximizing the value. No, that's not the correct answer. Anybody else? And Venkatesh, you might want to mute and lower your hand. Satvika?
Utility?
In some sense, but there's a statistical operator that corresponds to this definition. And Satvika, you might want to go back on mute and lower your hand. Anyone else? Sachin?
Is it the mean?
Yes, but it's the weighted mean. This is expectation. This is the expected value. Thank you very much, Sachin. That was a good answer.
Got it. Thank you.
So this is the expected value. This is the probability of getting this discounted sum of rewards. And we are summing those possible discounted sum of rewards weighted by their probability of occurrence. So, interesting. We know that we can define the value, the optimal value of state S using Q star with this equivalency. And we already know that Q star itself can be represented using this formula here. Now, we can combine these two and formulate the value of state S as a function of the value of the next state. This is a recursive formulation, right? We've already seen recursive formulations for our search algorithms. So to find the value of state S, we need to find the value of the next state. And to find the value of the next state, we need to find the value of the next state and all the way to the terminal states for which we already have the values. So this is called the recursive formulation of the value function, the optimal value functions. Before we move forward, any questions about this formulation? Okay. So remember this is the search tree for the racing game or the racing setting, right? This can go on forever and ever and ever, and the search tree can become really, really, really large and infeasible to represent. And of course, there can be different expansions of the tree. So for MDPs, even of the simple kinds like the racing game, we're just doing too much work with Expectimax. Expectimax was not designed to solve these sort of sequential decision-making problems. One of the reasons is in Expectimax, the states are repeated. So how can we solve this? We've already seen this. We can only compute the needed quantities once. There's another problem. In the racing game, the tree goes on forever. It's an infinite horizon game. So if we want to apply Expectimax, one idea is to do a depth-limited computation, but we increase the depth until the change in the obtained values are small. And note that the deep parts of the tree eventually don't matter if gamma is smaller than 1. What does that mean? It means that if we don't give the same worth to events happening in the future than those that happen right now, which means if gamma is not equal to 1, then the events that happen in distant future are not going to matter as much. Remember exponential discounting? If gamma is 0.1 in the second step, it will become 0.01. In the third step, it will become 0.001. And in the 100th step, it will become so small that we don't need to even care about the values that happen deeper in the tree or very far into the future. So let's talk about the idea of time-limited values. The key idea of time-limited values is that we define the v function for a particular time step k. We are going to say v sub k of state s, and v is the value function, is the optimal value of state s if the game ends in k more time steps, right? So what's the value of v0 of s? Anybody? Vivek?
It's already in the goal state. You don't have to go to the more steps of B0SS. It's already in the end of the game.
What is the value of it?
1.
You mean the value of the terminal state. Here's the thing. The rewards are obtained during transitions. So if you're in the terminal state or in a terminal state, you've already obtained the result, the reward associated with the terminal state while transiting into the terminal state. Now that you're in the terminal state, which means k is equal to 0, there's nothing else to do. There's no more reward to get. So the value, the v0 of a terminal state is 0. What about the v0 of any other state? It's the same, right?
Yeah.
So it's going to be 0. Remember, the rewards are obtained during transitions. When you say k is equal to 0, you mean that there's not going to be any more transitions afterward. So no more rewards are going to be obtained, and hence the sum of expected rewards is going to be 0. Vivek, did you have a question to ask? I'm going to assume no. Equivalently, we can think of this definition as the depth k expectimax value of S, or what would a depth k expectimax give from S. This is a similar graphical representation to what we've already seen for expectimax and depth limited expectimax. So let's look at an example of how we apply this time limited approach. I'll show you the algorithm later on, but let's see how it works. In the beginning, k is equal to 0. We begin from the terminal states. We can assign values to the terminal states because we already have them. Now, in the next iteration, we can assign values to those that are directly above the terminal level in the search tree. And we can keep this going. Note that these values are also changing along with the other values as they appear. And if we run this for 10 iterations, first of all, let's look at how it changes from 9 iterations to 10 iterations. There isn't a big change. There was a value of 40 associated with this state, 0.4. It becomes 0.41, and this one was 0.46. This becomes 0.48. The remainder mostly stay the same. Now let's keep going. 12 iterations, 100 iterations. And after 100 iterations, you will see only small changes in these values. If you see no changes at all, you will see that this iterative formulation, this expected max search is converged to the optimal values. So how can we come up with an algorithm based on this concept? What was the algorithm we ran to come up with these values in each iteration? That algorithm is called value iteration. So we start with V sub 0 of S equals 0. We said that V sub 0, in K equals 0, the value of every state is going to be 0 because there is no time steps left to obtain more results. So the expected sum of rewards is going to be 0. We start with this initialization. Now, in the next step, we do one ply of expected max from each state. We are going to calculate V sub K plus 1. So in the first step, after the 0th step, the first step is going to be 0 plus 1, 1 of each state is going to be the maximum achievable value. This is the same formulation that we see before. Is going to be the expected reward of following the optimal policy from state S, performing action A, and then the value of the next state, the discounted value of the next state. So this is what we had before. We are going to say that in each step, we are going to update our estimate of the value of S using this recursive formulation. Note that here we have V sub K, right? And in here we have V sub K plus 1. So in each time step, you're updating our estimate, our initial estimate of the value of the state S based on our previous estimate or our current estimate of the value of the next state. And we repeat this process until convergence. Now, how complex is this algorithm? Each iteration, in the worst case, the O notation, is going to be in the order of S squared, where S is the size of the state space, multiplied by the number of actions available. Why? Well, remember, in here, we are iterating over possible states that can be reached from the state S. And we are finding the maximum action, the maximizing action. So we are iterating over all actions as well. This is so far S times A. Where does the second S come from? Why is it S squared? It's because we are calculating V for all states. So V needs to be calculated for all states. V is a function whose domain is S. So it becomes of the order of S squared multiplied by A. And that's for each iteration. This doesn't seem like a very feasible approach for large problems, but it's a good stepping stone. It's a good starting point. Now there's a theorem that says this value iteration algorithm will converge to unique optimal values. And the basic idea behind the proof is approximations get refined towards optimal values. But note that the policy itself, the optimal policy, may converge long before the values do. This is something that we will use later on in our discussion of policy iteration later on. Any questions about the value iteration algorithm? You should be full of questions at this point. Any questions about value iteration? Okay. So if you're curious, Shantanu, yes? Shantanu, I can't hear you. Hello? I'm sorry, Shantanu, I can't hear you. Still no sound. So, Shantanu, would you like to write your question in the chat box? And I will ask Bibek to read that question to me. Bibek, can you read that question?
So Santano is asking how they have calculated the complexity.
Oh, I was explaining how it was calculated. So once again, thank you, Bibek, and thank you, Shantanu. Once again, in here, see this summation? This summation is over all the states that can be reached from state S by taking action A. The worst case scenario is all the states are reachable. There's a possibility for all the states in the environment to be reached when you are in state S in action A. So worst case scenario, this will happen for at least S times. S is the size of the state space. Now in here, we are looking for the maximum achievable value, and that max depends on your choice of A. So you will be iterating over all possible actions as well. That's where A comes from. Now remember, we are calculating V as a function, right? So V is defined for all S. So we have to repeat this process for all states in the state space. That's where the second factor of S comes into play. It's going to be S multiplied, S, the first S coming from here, the second S coming from here, S squared multiplied by the number of actions that needs to be iterated over to find the max A. I'm sorry, I can't see the chat box. Bibek, can you tell me what the latest message is? Bibek?
There is nothing in the chat box, Professor.
All right. I thought I saw something coming in the chat box. Okay, thank you. Now let's take a quick look at the value iteration algorithm for the racing game. So for k equals 0, all the states are going to be assigned a value of 0. That's based on the definition of reward and value function. Now for v equals 1, for each state, we are going to put in the corresponding values. So the transition probabilities are these 0.5, 1.0, 0.5, and so on for each state, and we'll find the maximum possible. We'll add them up. And this V sub k of S prime for all states is going to be 0. This is V sub k for k equals 0 for all states. And then in the next iteration, in k equals 2, we'll get to these values. We can continue this to see if it changes. I think the last time I tried this, the values don't change that much. So in 2 or 3 iterations, we reached the, we converged through value iteration. All right, so let's take a 5-minute break and come back at 4:45. If you have any questions at this point, you can ask either via audio or in the chat.